an object from beyond our Sun, 3I Atlas, is now slicing through the Martian neighborhood. Early orbital models hint at a dangerous possibility. Is Mars truly in danger from a hyperbolic collision? Or is the data simply deceiving us? We break down the math of orbital solutions and map the critical difference between a close pass and a true impact corridor. Here's what NASA watches for in the weeks ahead. Is Mars actually in danger from 3I Atlas, or is this a misread orbit? That's the question we'll answer. In plain terms, we'll define 3I Atlas, an interstellar object, explain how orbital solutions work, and map the difference between a close pass and a true impact corridor. By the end, you'll know what NASA would do if a risk were credible, and what astronomers watch for in the weeks ahead, what 3I Atlas is, and why its orbit looks so strange. An object from beyond the Sun's reach now seems to skim the Martian neighborhood. So with only a handful of measurements, how do astronomers know if that line on a chart means a pass or a hit? Start with the basics. 3. I-Atlas is labeled interstellar because its path is not closed around the Sun. In plain terms, it follows a hyperbolic trajectory. Hyperbolic means the orbit's eccentricity is greater than 1, so gravity will bend it, but not capture it. It is a one-time visitor. That alone makes the motion look odd compared to the loops we see for planets and most comets. When you plot it, the track slices through the inner solar system and out again. The shape can trick the eye, especially when the time axis and the distance scale fight each other on a small screen. Here's where early math gets jumpy. At Discovery, we might have positions from a few nights. Each position comes from astrometry, which is the precise measurement of where the object sits against background stars at an exact time. Feed those points into a least squares fit, and the computer solves for the orbit that best matches the data. The fit also spits out uncertainties, often shown as covariance ellipses, error zones that tell you how much the answer can drift. When the arc of observations is short, those ellipses are long and skinny. Move forward in time, and they balloon. A millisecond off in timing, or a fraction of an arcsecond off in position, can fan out into millions of kilometers weeks later. That is why early impact track graphics can mislead. A single colored line looks decisive, but it ignores the spread. A close approach means the central, most likely path passes near a planet. Impact probability asks a different question. How much of that uncertainty volume overlaps the planet's size at the moment of encounter? An impact corridor drawing is not a prediction line. It maps where on a planet an impact could occur if the object were actually on one of the edge cases inside the error region. If the error shrinks and still overlays the planet, risk grows. If it shrinks off the limb, risk drops. Think of a flashlight aimed across a field. Right at the lamp, the beam looks thin. Far away, the circle widens. With just a few observations, the beam is wide by the time it reaches Mars's distance. As more nights pile up, you narrow the lamp, and the circle tightens. There is another wrinkle. Small bodies can feel non-gravitational forces. For comets, outgassing, jets of vapor and dust as the surface warms, acts like tiny thrusters. If we assume pure gravity at first, then activity turns on. The object drifts from the predicted line. Interstellar objects may have unusual compositions or spin states, so their outgassing, if any, can push in unexpected directions. That does not mean chaos. It means the model needs extra terms, and those terms need data to constrain them. So, what do we watch for as the fit improves? Two clear outcomes. With additional astrometry and, if possible, light curves that hint at rotation and activity, the solution will either pull the corridor away from Mars or concentrate it. A working hypothesis, based on most past alerts, is that uncertainties shrink off the planet as the arc length grows. Alternative scenarios, late onset activity, or a weird spin axis, could delay that convergence, but they still leave fingerprints in the measurements. The consensus view in planetary defense is cautious and methodical. Wide uncertainties are normal at the start. A credible hazard requires repeated independent measurements that pull the error ellipses down onto the planet and keep them there over multiple nights. That has not occurred so far. The next steps follow from that reality, and they matter because action depends on thresholds, not headlines. Now that the math behind the orbit is on solid ground, let's look at what NASA would do if those thresholds were actually crossed for Mars. If the risk were real, what NASA and observatories would do. Next, suppose the uncertainty corridor did tighten toward Mars. What switches would flip across NASA's planetary defense network, and how fast would they move? First, the players. The Minor Planet Center acts as the clearinghouse for observations. Observers upload astrometry, which are time-stamped positions against background stars. JPL's CNEOS Sentry system takes those data and runs impact monitoring, computing many virtual versions of the object to map risk. NASA's Planetary Defense Coordination Office, the PDCO, handles alerts and coordination if risk crosses set thresholds. In Europe, ESA's NEO Coordination Center mirrors these functions and provides independent checks. Together, this forms a loop. Data in, risk assessed, guidance out to observers and mission teams. Now, the complication. Interstellar status means a hyperbolic path and higher speeds. That alone strains typical models. Add non-gravitational forces, tiny pushes from possible outgassing, plus unknown rotation, and small mismodeling can grow fast. A working hypothesis is that such forces remain small until the object warms, but alternatives include intermittent jets or spin axis flips that bias the orbit fits. Modelers need to test gravity-only solutions against activity-enabled ones and watch which track the data best. Verification starts with rapid follow-up. Observatories across longitudes pick up nightly astrometry to extend the arc. With each new night, the least squares fit tightens, and the covariance, the error shape around the solution, shrinks. If geometry allows, planetary radar comes next. Radar ranging gives direct distance and speed, cutting uncertainty sharply, but only if the object is close enough and bright enough to radar systems. Photometry, which measures brightness, changes over time, reveals rotation rate and hints of activity. A spin period can modulate jets. That pattern helps add reliable non-gravitational terms to the orbit model. Analysts then reprocess everything, update the ephemeris, and push fresh predictions to Sentry and the community. Here's a case study for context. When NASA's DART mission targeted Dimorphos, teams relied on precise ephemerides, which are detailed tables of position and time. The target was bound to the Sun, well observed, and slow compared with an interstellar visitor. That allowed fine navigation and a planned impact. With a fast hyperbolic newcomer, you get less warning, higher closing speed, and fewer chances for radar or spacecraft recon. The lesson carries over though. When the ephemeris is solid, action can be precise. The challenge is getting there quickly with an object that may change behavior as it warms. Mars adds its own factors. The atmosphere is thin, so most small bodies reach the ground, but they also fragment differently. Dust mobilization matters because sharp pressure waves can loft fine grains and affect solar panels and optics. Still, mission teams put orbiters and rovers into safe modes only after a demonstrated hazard. That means a high enough impact probability, a narrow time window, and a predicted footprint that intersects Mars. Protecting assets prematurely can cost science time, so operators wait for hard thresholds. What are those thresholds? They vary by mission and timing, but a rising impact probability into the single-digit % range at a defined epoch would trigger higher alert states and contingency planning. As confidence grows, teams might reorient orbiters to reduce risk to instruments, adjust communication passes, or park rovers to protect mast cameras. Observation campaigns around Mars would spin up to watch the atmosphere and surface for dust effects if the object were large enough to matter. Expect a days to weeks cadence for tightening the orbit. Each new observing night shifts probability regions. Sometimes they slide off the planet. Sometimes they drift closer before turning away as more data arrive. The consensus view is steady. Keep observing until uncertainties fall below actionable levels or risk becomes clear. Today's measurements do not meet action thresholds, so the protocol stays in watchful waiting with targeted follow-up to close the gaps. As fresh astrometry posts to the Minor Planet Center and new Sentry runs appear, watch for two signals: a shrinking corridor that no longer touches Mars, or a stabilized overlap that holds across multiple updates. Conclusion: the path to certainty is more data. Early interstellar orbits look dramatic because they are hyperbolic and fast, but credible impact claims must survive repeated measurements and shrinking error bars. That is the consensus. Track updates through JPL's small body database and CNEOS impact tables. Favor sources that publish uncertainties, observation arcs, and covariance details, not just a single line on a sky map. If you see a corridor graphic, check the date and the stated probability. We will update as the arc length grows. The next few observations will show whether this becomes a close pass story or a real hazard test for Mars and its spacecraft.